of wireless media, and then we move on to the next topic of signal encoding techniques. Similar, we went through examples of wired media. We went through twisted pair, coaxial cable, optical fibre as three examples of common wired media. Let's quickly go through three examples of wireless media just to give some typical applications of wireless. And I think you know of these already. That's why we'll be quite quick. First, one thing that you may have seen is, or you've seen and at least used in a number of cases, is what we refer to as terrestrial microwave, where terrestrial means on the ground. Now this is wireless. The signal's not on the ground, but the transmitter and receiver are on the ground, as opposed to the next one, which is satellite microwave. What does microwave mean? I think last week I said it refers to the wavelength. That's not right. It's not about the wavelength of the signal. It's just a general name for the range of frequencies of around, I think it's one of the earlier slides, of around 30 megahertz up to tens of gigahertz. So the range of frequencies. Sometimes we talk about the visible light spectrum or the infrared spectrum, and another one is the microwave spectrum. It doesn't mean the wavelengths are micrometers. So it refers to a general portion of the spectrum, a range of frequencies. Terrestrial, on the ground, meaning our transmitters are on the ground as opposed to up in space. A typical example is point-to-point links, where you have a parabolic antenna, a dish antenna, let's say on the top of, and it is on the top of this building, we have a dish antenna, and at Rangsit campus we have another dish antenna there on top of one of the other buildings pointing at each other, and they form a wireless link between the two campuses. So across that distance of, 12 or 15 kilometres, we have a wireless link between our two campuses using terrestrial microwave is the general technique. So there are antennas that are several metres in diameter. I think ours is just a 1 metre antenna, maybe smaller. And they are highly directional antennas in that the signal is concentrated in one direction. You need to point the antennas at each other. If you misalign the antennas, then they will not be able to receive the correct signal, receive the signal from the transmitter. Generally require line of sight communications. So we have a link between our two campuses, and if you go up and on the top of this building, you should be able to see the other building at the Rangsit campus where we have the receiving antenna on. If someone comes and builds another building, builds another building which is 10 stories high next to us, and then potentially we cannot link wirelessly to our other campus because our signal will probably not go through the concrete of the next building. So normally we place the antennas up high to avoid any obstacles between the pair of transmit and receive antennas. So on large buildings, on large towers is the typical location for antennas. Used for long distance communications. Communications between buildings, for example. Ours is one example. Between our two campuses, we have a wireless link. As an alternative, in fact, in our case, it's as a backup of the wired link between the two campuses. So you can use it as a backup in case the wired link is not available, or use it together with the wired link. What's the advantage of having a wireless link between our two campuses as opposed to using a wired link? Anyone? What's an advantage for us, for SIT, for having a wireless link between our two campuses? Save on Okay, we can increase the speed, or if we have both, assuming that they're the same data rate. What else is an advantage? Yeah.
Save cost from this line if are using WAN.
Yeah. We don't own the wired link between the two campuses. We lease access to the line from a telecoms company or an internet service provider. So the link between this campus and Rangsit campus, we pay, I don't know who we pay, someone like TOT or CAT, we pay someone to use their cables and we send the data through their cables. So we pay for that access. But with the wireless link, we own the transmitter on this building and we own the transceiver really on the other building, and therefore we do not have to pay anyone for using that link. So there's an advantage of using wireless if you have, you do not need to get access to the wired network. And in cities, well, the other alternative, if we don't want to pay a company to use their wired network, we could build our own wired network. But that's very expensive. You need to get access from different companies to dig holes under the ground and lay the cables. It's a very complex, time-consuming and expensive task to build your own wired network. But with wireless and point-to-point link, if you want to connect two locations, you just need two antennas on your building, so long as you have line of sight, then, and within some distance, I don't know if we give examples here, but normally tens of kilometres, then you can have a direct link. TV transmission is an example of this. Instead of using optical fibre in some cases, especially in remote locations or in cities where you cannot build a new network, then using wireless makes sense there. Your mobile phone systems also fall in this category as well, using the same range of frequencies. But of course, they're not point-to-point systems, they are point-to-multipoint. There's one mobile phone tower sending to many people's mobile phones. We're talking about data rates in the order of tens of megabits per second, usually distances of kilometres to tens of kilometres. A mobile phone tower will normally provide coverage with a radius of maybe kilometres, several kilometres. The link between our two campuses is about 12 or 15 kilometres, maybe 30 kilometres for some wireless point-to-point links. Using frequency bands around from about 2 gigahertz up to 10, 20 gigahertz. So one example of wireless media using either point-to-point links over a long distance, or in some cases point-to-multipoint, for example TV distribution and mobile phone systems. Another example, terrestrial means on the ground, where the transmitter and receiver are on the ground. Satellite microwave, now we have something up in space, a satellite. So some communication satellite acts as a relay station. We have, in fact, we still have the transmitters and receivers on the ground stations. One of them transmits up to a satellite, and then the satellite transmits down to another receiving station. So they link, the satellites link 2 or more ground or earth stations. We'll talk about the links with some examples in a moment. The location of the satellite is important and has an impact upon the service it can provide the users. So the satellite is up in space, but because the Earth is turning, then where the satellite is relative to the Earth has an impact of whether the satellite is moving relative to the Earth. A geostationary orbit of a satellite, a geosatellite, the satellite is is launched and located in an orbit such that as the Earth rotates, the satellite is also rotating. So when I look up, it's as if the satellite is not moving. As the Earth is rotating, the satellite is rotating at a rate such that it provides constant, or it's always above the same point at the same time. And the location is that it's to achieve that the orbit's about 36,000 kilometres above the Earth. So that's a geostationary orbit satellite. As a result, if you're going to imagine the satellite is up high, when it transmits down, it covers about 1/3 of the surface of the Earth. When it transmits down, we'll see some pictures in a moment of a footprint. If here's the Earth, if the satellite is up high, all right, then it's got coverage of this portion of the Earth. And as the Earth rotates, the satellite is also rotating such that the satellite always has coverage of the same portion of the Earth. There are other orbits at lower positions. For example, a low Earth orbit, a LEO satellite, usually hundreds of kilometres above the Earth, so much closer. What that means is as the Earth is rotating, these satellites, these LEO satellites, are going around much faster. Because they're closer, they are, from the perspective of the ground user, they are moving above us. They're not in a fixed position. So if I look up, I will see a LEO satellite. If I can see the satellite, I would see it and would see it as moving. And eventually, after some time, maybe tens of minutes, it would be out of range from my position because it's gone around the other side of the Earth. And the disadvantage of that is that we do not always have constant coverage with a single satellite of the same portion of the Earth. With a geosatellite, it's always providing coverage of this part of the Earth. For example, always providing coverage of Asia or a portion of Asia. And we can provide service to all the users there. With a LEO satellite, it's moving around, and if we have a user here, then a ground station, then maybe for 10 minutes or 1 hour, then that LEO satellite can connect to the ground station and provides coverage there. But for the rest of the time, it's on the other side of the Earth, and of course cannot transmit to here because it's cannot transmit through the Earth because we need line of sight communications. So although a geosatellite can provide coverage of about 1/3 of the Earth, a LEO satellite, we're talking about a footprint that is coverage area of several thousand kilometres, much smaller coverage area. So many of the satellite services we use or are available today use geo satellites, but there are satellite services using other orbits, including LEO. Maybe 10, 15 years ago, there were plans to build constellations of LEO satellites. Because one only covers a small portion of the Earth, the footprint is much smaller, as it only covers this portion, then the idea is to put many satellites up. Such that they cover all of the Earth. And of course have them all the way around. So that even though they're moving, this point currently has coverage from this LEO satellite. As they move around, we'll move into the coverage of the next satellite and the next one and so on. But that's very complex to provide service and quite difficult. So there are several systems that do that, but not as many as they originally planned. So there are different orbits of the satellite. One of the problems with a geostationary satellite is the propagation delay. 36,000 kilometres. Propagation delay, remember, is distance divided by the speed of light, c. 36,000 kilometres. That's to transmit a signal up to the satellite. The propagation delay is 36,000 kilometres or 36 million metres. Speed of light, 300 million metres per second. Is 0.12 seconds. Correct? 120 milliseconds is the propagation delay. That is, when I transmit up to the geostationary satellite, the signal will take 120 milliseconds to get there, and of course it needs to come down to some other ground station as well. We transmit up from one ground station to the satellite transmits down to another one. So up is 120, down is 120, about one quarter of a second is the propagation delay, 240 milliseconds. We cannot avoid that. Propagation delay is, we cannot minimise it, depends upon the distance. The reason we have it so high is that we get this orbit such that we get constant coverage of one point of the Earth, but we have a high propagation delay. When you start to use internet applications, voice calls, web browsing and so on, and you use geostationary satellites, this delay can start to have an impact on our applications, because a delay of propagation of 240 milliseconds plus other delays makes some applications not work well. It adds a quarter of a millisecond delay to all of your web browsing. That doesn't include the delay through the internet on the ground as well. So it adds a large delay to your application which you cannot avoid. That's the problem with a geostationary satellite. So the approach, we have an uplink, we transmit up from a ground or earth station to a satellite, and the satellite usually just relays that signal and transmits the same thing down, and it's received by a different earth station somewhere else in the world within the coverage of the satellite. Let's say an earth station here and here. As a result, we can transmit across a large distance, about 1/3 of the Earth, using the satellite, as opposed to using wired network or terrestrial microwave. This is in a point-to-point link configuration. Let's say we have our ground station here in Thailand and another ground station here in Hong Kong. Then to transmit between the two ground stations up to the satellite, and then the satellite transmits down and is received by the ground station in Hong Kong, as opposed to sending via cables or via some multiple wireless links. Very easy to provide coverage across a large area. Another approach, and this is what's used, for example, for satellite TV, there's one transmitter that transmits up to the satellite, and the satellite transmits down in a broadcast configuration. That is, it sends to everyone within the coverage area or the footprint. There are multiple receivers. The TV station has an earth station or sends their TV content to an earth station which transmits up to the satellite. The satellite transmits down. Everyone who has a dish who's within the coverage area of that satellite can receive the content. So this is a point to multi-point configuration, sometimes called broadcast. We're sending to many as opposed to one. So where do we use satellites? TV distribution, some long-distance telephone communications, private business networks. Let's say 7-Eleven throughout the country puts small antennas, referred to as very small aperture terminals, VSATs, on each of their shops. so that they can communicate and exchange data between all the 7-Elevens, then they can connect them all together by using a single satellite, as opposed to paying for cabled links all through the network. GPS is another example, where we have multiple satellites providing some positioning service. One example, IP Star, or the satellite's called ThaiCom-4. It's a Thai satellite which provides internet service to large parts of Asia. It's a geostationary satellite, so it's sitting about 36,000 kilometres above the Earth. It was launched in 2005. It should last, or they expect the satellite to last for about 12 years. Without any fuel, the weight of the satellite, so the size of the satellite, is about 3.5 tonnes, 3,400 kilograms. So it's a large satellite. And as a result, because it's large and you need to get it 36,000 kilometres above the Earth, there's a high expense in both building the satellite and launching the satellite. Okay, so that's with satellite communications, a large cost is getting the satellite up there. Provides a capacity of a total of 45 gigabits per second. It separates that into different applications, but it can transmit at 45 gigabits per second. It transmits actually signals at different frequency ranges. And there are different names for some of the bands. One's called KU and KA. They just refer to specific frequencies in the orders of tens of gigahertz is the frequency range. And the next one shows, well, that's the configuration. This diagram shows the spot beams, or the footprints of the satellite. That is, it has multiple antennas on it transmitting, not just one, has multiple antennas called, or can transmit multiple signals in different directions. They're called beams, and different types of beams. And this satellite is configured such that it has these three shaped beams. That is, it transmits down to the Earth, covering three different areas which it can control. And you see them here. Here's Australia, here's Southeast, or part of Southeast Asia, Indonesia, and here is China. So it's got coverage of those areas with those three special beams. Then 84 spot beams. So again, you think of 84 different antennas pointing in particular directions. And they are the blue shapes here, or actually the highlighted blue, you can see, in fact, if you look closer, there are some circles and ellipses here. So there are 3 spot beams over New Zealand. And through Asia, Thailand and so on, there are many different spot beams. And if you're within coverage of them, then you can use this satellite, and they provide an internet service. IP Star provides satellite internet service, where you have an antenna at home like this. It's about, I think it's about this big, so about 0.5 metre diameter. You have a modem, essentially, that connects into that, and you can transmit up to the antenna and receive from the antenna, and so transmit up to the satellite, receive from the satellite, which connects to one of several ground stations, which then connects to the internet. So you get internet access, especially where there's no landline, fixed wide internet access. So that's an example of one satellite communication system. And the last example, so that was IP Star. You can see it on the website. That's where the other pictures came from. It gives in there, you can find the specifications like the transmit power, the frequencies of the used by the terminals. The other is generally, so terrestrial microwave, satellite microwave are two examples of wireless media. The other generally referred to as broadcast radio. So using frequencies of 30 megahertz up to 1 gigahertz, whereas the microwave examples we saw before are usually 1 gigahertz up to tens of gigahertz. Broadcast means transmit to multiple receivers. Some examples: FM radio, UHF, VHF, TV, Wi-Fi, wireless LAN is an example of this, where we transmit our signal and anyone within range can receive that signal. Hopefully there's an access point in range, and then that access point uses the wired network to send across to some other destination. So Wi-Fi is an example of a broadcast radio technique. We're not going to go through any detail of how Wi-Fi works. Some of you may cover it in a topic next semester. I cover it for the IT section on internet technologies. But just 3 examples of wireless media. Which brings us to the end of this topic. Any questions about those 3 examples? The main part about the wireless media is the concepts that we went through yesterday about this path loss, which can be applied to all of these 3 examples. How do we lose signal strength across distance? We went through them quite quickly because we've got this one final topic to go through, or a portion of this next topic. So you can answer questions in the exam. So we've spoken about signals in the topic on data transmission. We saw, okay, signals are made up of sine waves. We can combine them together. We gave some examples, remember, of calculating the data rate given the frequency and bandwidth. We looked at, okay, we said if the signal is high, that represents 1 bit. If it's low, another bit. But remember, we also said we could have an alternative scheme where we could have 4 levels, where we could have high, +1, I think we had plus 1/3, minus 1/3, and minus 1. We have 4 levels where each level corresponded to 2 bits. And you remember that with that case, we increased the data rate by encoding 2 bits into one signal element. With the same signaling rate, we got a higher or double the data rate. That was a scheme for how do we encode our data into a signal. And that's what this topic is about. And more detail of how do we encode data into signals. And we'll see there are many different schemes. They depend upon the type of data we're sending and the type of signals. We want to transmit signals such that we optimize the use of the transmission medium. If we have a wireless transmission medium, we can transmit at a particular bandwidth. We want to get as much data through that medium as possible using the limited bandwidth. We want to conserve the bandwidth and minimize errors. We also know that if there's noise in the system, which there always is, there's more chance of errors. We'd like to have a signal encoding scheme or technique that deals with this. Recall there are 2 types of signals, analog or digital. And we've got 2 types of data, analog or digital. So what we do is we take our data and convert it to a signal that can be transmitted. Digital signaling is when we send a digital signal. So if we have digital data, we encode it into a digital signal. Or if we have analog data, like voice, we can encode it into a digital signal and transmit the digital signal. An analog signal is when we use analog signals, either digital or analog data. We transmit some analog signal at a particular frequency. And I think we will not get to cover this today. It will be after the midterm. We talk about we've got different terminology for the types of the signals, analog signals especially. Today I think we'll just get to cover one part of digital signaling. So with digital signaling, when we transmit a digital signal, so here's our source, we have some data. That data can be either digital or analog. If we want to transmit a digital signal, we use an encoder. We encode the data into a digital signal, a set of pulses, and transmit that signal from the source to the destination. At the destination, it receives a digital signal and uses a decoder to get your data back, whether it was analog or digital data. So this is the process of encoding onto a digital signal. We have an encoder and a decoder, or a coder and decoder, or combined called a codec. So that's what a codec comes from. So this is the signal, or an example of the signal we send, a digital signal sent between the source and destination. When we're using an analog signal or analog signaling, we have our data and we're going to send an analog signal, usually centered around a particular frequency. And we'll call this the carrier frequency. We're going to use an analog signal of some frequency to carry our data, whether it's analog or digital data. So what the process is that we take our data and using some input carrier frequency, we modulate the data onto that carrier frequency. Transmit some analog signal, the receiver receives that and demodulates it to get the original data back. Modulator, demodulator, that's our modem. Today we'll just look at a codec. I think that's all we have time for. So we have 4 combinations, remember. We've got either analog or digital data, and we need to send it as either an analog or digital signal. So we get 4 combinations of what we can use. We'll go through one of them, maybe the second one today. Just a quick comparison of the different options, the advantages and disadvantages. If we're using all digital, our data is zeros and ones, and we send pulses, a digital signal. What's the advantage? Normally today the equipment to do the encoding and decoding is much less complex and expensive than converting to an analog signal. So digital data and sending a digital signal is generally cheaper than converting our data into an analog signal. That's one advantage there. What about using analog data, sending a digital signal? Well, the advantage of that, of converting from one to another, from analog into digital, is that we can take advantage of the digital transmission equipment. Again, of digital transmitters, which are generally cheaper to build, to implement, and to deploy than analog transmitters. We can use repeaters as opposed to amplifiers, and it's better in terms of reducing bit errors. So there are advantages of using digital transmission equipment, sending digital signals, even if we have analog data. So sometimes it makes sense to convert the analog data into digital data, digital signals. But sometimes we cannot send digital signals. It makes sense to send analog signals. Some media only propagate analog signals. Optical fibre and wireless. Wireless, we're sending an analog signal from my laptop to the access point, even though we may want to send digital data. So we need that case. And the other case is, or the final case is, what if we have analog data? Well, sometimes we'd like to send an analog signal. It may be very easy to do so. For example, with voice, the analog data, my voice ranges in frequencies of up to about 4 kilohertz, so 0 up to 4 kilohertz. And it's very easy to transmit that voice across a copper wire by transmitting that exactly as is. So transmitting a signal with frequencies from 0 up to 4 kilohertz across a copper wire. We don't need to do any conversion. We just take the analog, convert it to the analog audio input, convert to some electrical analog signal and transmit. And that's what our home telephone does. It takes your voice and converts it to an electrical signal and sends it at the same frequencies across the copper wire. So it's very easy to do that because we can use the same frequencies. And there's some other things that we can do by converting and combining signals from multiple sources and sending them at different frequencies. We'll come back to this one after the midterm. Today we'll look at sending digital data as a digital signal. How do we do it, or how have we done it in our examples in the past? What do we do? I have zeros and ones. What do I transmit as a signal? We've seen several examples in the past. What do I transmit if I want to transmit a 0 in terms of my digital signal? Anyone? We've drawn examples which look like we send some voltage pulse, so we send some pulse at some particular value, so some voltage at some plus 1 volt for one level and say -1 for a different level. We get things, we've drawn pictures like this, where this is our signal, where we transmit, say, some voltage, -1, +1, where this represents one bit and this another bit. That's a signal encoding scheme of sending digital data as a digital signal. This is the digital signal, and the digital data, if it was 0, 1, 0, 1, 0, would map to this signal, where the scheme says when you have bit 0, send a low level. When you have a bit 1, send a high level. And if we have a different sequence of bits to send, then we just follow that scheme. We send a pulse for some period of time that corresponds to the level that the scheme describes. So this is a signal encoding scheme, the simplest one that we've used in examples. We'll see there are others. The schemes must be known by the transmitter and receiver. Okay, they must be agreed upon. So the transmitter and receiver must know which scheme is being used, and also the pulse duration. We've called this a signal element. Let's say it's a duration of 1 millisecond, for example. So the transmitter transmits a signal at one level for 1 millisecond, corresponding to bit 0, and now it has a bit 1 to send, so for a 1 millisecond it transmits the signal at the other level. So the transmitter and receiver must know the duration of the signal element, of the pulse. So we have a sequence of discrete voltage pulses at different levels. We refer to each pulse as a signal element, and we encode our binary data onto signal elements or into signal elements. This is one example. The data rate is how many bits per second we send, and we've talked about the signaling rate as the number of signal elements per second. In this case, the data rate and the signal rate will be the same. But in another case, we could have multiple bits for each signal element. Or we could have multiple signal elements for a single bit. So there's a difference between the data rate and the signaling, or sometimes called modulation rate. We've seen this before. When we send our signal, which represents some data, there's some noise in the system. The noise impacts upon our received data. Some of the things that we've found out that, what was one of the, all right, we know that when we increase the bandwidth, we can get a higher data rate. We've done some analysis that showed or gave some examples of that. More bandwidth, more data rate. Although not mentioned here, generally more bandwidth, the more noise can come into the system. The more noise, this is the signal to noise ratio, as the noise goes up, there's more chance of bit errors. Okay, we've seen that as well, that as the noise increases, there's a more chance of changing our signal from one level to the wrong level. So the more noise, that is, the higher the signal to noise ratio, this is correct what I'm saying. The more noise, the more bit errors, but what we're saying here is that the increase in the signal to noise ratio decreases the errors. So remember, signal to noise ratio is signal divided by noise. If noise goes up, then the number of errors, the bit error rate, goes up, because the signal to noise ratio goes down. If the signal strength goes down, the signal to noise ratio goes down, this value goes down, and the number of errors goes up, which is here. An increase in the signal to noise ratio decreases bit error rate. Another thing, an increase in the data rate increases the bit error rate as well. You can almost see that in this plot. If we have this noise, we saw that this impulse of noise here caused 1 bit error, because it lasted for a duration of about 1 signal element. And so did this one. This large negative amount of noise here lasted for about 1 signal element. But if we increase the data rate and increase the signaling rate, then the same amount of noise could impact upon 2 signal elements, or 3 or more signal elements. If we send more bits in the same amount of time, then the same amount of noise can cause errors for more bits. So higher the data rate, the more errors, the bit error rate. So these are some of the factors that impact upon how successful our data reception is. The other thing, which is what we're going to look at, is how do we encode the bits into signals, the encoding scheme. And what we're going to do is look at some example common encoding schemes. They are described here. Some examples are here. I'm going to go through some of those examples on the board here. So you don't need to copy down the examples on the board. I'll go through these ones or some of these ones here. The first scheme, and is the most common one that we think of, is, well, in fact, the opposite of this one here. Here we had a scheme of bit 0, transmit low level, bit 1, high level. A very common scheme is called non-return to zero level. The non-return to zero means do not return to 0 volts, which is in the middle. That is, alternate or go between a positive voltage and a negative voltage. And the most common definition of non-return to zero is that for bit 0, transmit at a high level and a bit 1 at a low level, which is just the opposite of this. Okay? So long as the transmitter and receiver know which scheme, then it's okay. So with our data here, actually I won't draw it because it's, I think, so easy, but with bit 0, we have a high level, we'd send high. So if this dashed line in the middle is 0 volts, we'd send high, low, high, high, low, low, high, 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 low, low. So bit 0, transmit a high voltage, a positive voltage. Bit 1, transmit a negative voltage. That's all. That's the scheme that we've seen in examples, or that's sometimes the opposite of what I've used in the examples. Non-return to zero, meaning we go between a positive and a negative voltage. We don't transmit at a 0 voltage. We'll go through the schemes and we'll talk about some trade-offs between them after we've gone through the schemes, some advantages and disadvantages. Another one is non-return to zero inverted. The rules are when you have a bit 0, no transition at the beginning of the interval. And a bit 1, you have a transition. You change from a negative to a positive, or from a positive to a negative, depending on what the last value was. Let's try and draw that here. So again, we're not going to return to 0. We're going to go between a low level and a high level. When we have a bit 0, we do not change the level. There's no transition. We maintain what we had in the previous bit. But when we have a bit 1 to transmit, we will change the level from high to low or from low to high. We need to assume we start at some level. Let's assume, and to get it the same as this one, we're going to assume we start at the low level. So assume we have a low level here. When we have a bit 0 to send, we do not change the level. So we maintain that low level. When we have a bit 1 to send, like we do now, we invert. We have a transition. We change from low to high and transmit for the duration of the pulse. When we have a bit 0 to send now, so that's the first 2 bits, a bit 0 to send, we do not change the level. So we maintain at the high level. Bit 0, maintain the level. Bit 1, transition or invert. Another bit 1, transition. Bit 0, maintain the same level. Bit 0, 0, 1, we have a transition, and another 1. So this is non-return to 0 invert on 1s. Did I get it correct? That's this second example here. So a different signal encoding scheme where the digital signal is we maintain a level if we want to transmit a bit 0, and we invert or perform a transition if we want to transmit a bit 1. Non-return to 0, we do not send at 0 volts, we go between a negative and a positive voltage, doesn't matter the values. Inverted, meaning we invert on 1s, on bit 1s. Let's go through some different examples. So they're maybe the two simplest schemes. Bipolar AMI. When we want to transmit a bit 0, we transmit at 0 voltage. So no line signal. So we do not transmit at a positive or a negative voltage. When we want to transmit a bit 1, we transmit at a positive or a negative level, and we alternate between them as we get to new bit 1s. So again, we need to assume that we start at some level. Let's say we assume we start at low. We'll see why that's needed. When we transmit, actually we don't need to draw that there. We'll see it with a bit 1. When we transmit a 0, we send at 0 volts. No line signal. When we transmit a bit 1, we send at either a positive or a negative, but we alternate. So assuming before we had a low level, then the next bit 1 would send at a high level. Bit 0 at 0 volts, bit 0 at 0 volts. The next bit 1 at a non-zero level, the opposite to the previous bit 1. This was at high, so we go down to low. The next bit 1, we go from a low level up to a high level. 0, back to 0 volts, 0, 0. Another bit 1, previous bit 1 was high, this one will be low and high. Bit 0, 0 volts. Bits 1 alternate, high, low, high, low, high, low, and so on. Assuming the first bit 1 has to be, in this case, at high. So that's bipolar AMI, alternate mark inversion, where the mark represents, say, bit 1 here. We invert the level for bit 1s for alternate bits. So high, low, and so on. We're inverting the levels. If we're using bipolar AMI and you receive a signal, and this is the signal you received. If we follow on here, if you receive this signal, I'll mark. After noise, so all right, I haven't drawn the noise in here, but if this is what is received, what are the bits that you've received using bipolar AMI? 0, because it's at 0 volts. 1, because it's a non-zero voltage. Here, 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 here. Something's gone wrong. When we use bipolar AMI, when we transmit, we should alternate, but when we're sending bit 1s, between high, low, high, low, high, low. If we receive a signal which does not alternate, here we have high, low, low, something has gone wrong between the transmitter and receiver. The receiver knows that this signal received is incorrect. It has detected an error in the data that's been transmitted. Maybe what went wrong is that one of these preceding zeros should have been a bit 1. Maybe noise changed the level, some error in the system. The point here is that with this bipolar AMI, using this signal encoding scheme, we can detect errors at the receiver. And that's good, because when we have errors, if we detect them, we can respond somehow. So an advantage of some of these schemes is the inbuilt error detection. Pseudo-ternary is almost the opposite of bipolar AMI. On bit 0, we have a positive or negative level, but we alternate on successive zeros. And at bit 1, we have 0 volts. One more example. There's Manchester, where when we transmit a bit 0, we change from, during the signal pulse, we change from a high to a low level. And when we transmit a bit 1, we change from a low to a high level. I'll not go through the full example. We'll go through differential Manchester. But you can think of Manchester encoding as, if you want to send a bit 0, you send a signal. If this is the duration of the pulse, you send from high to low. You send a signal which there's a transition in the middle of the signal element from high to low. Maybe to make that clearer, this is the signal. And with a bit 1, from low to high. That's seen in this encoding. Bit 0, we see, so now we're having a transition in the middle of the pulse, or in the middle of the signal element. We go from high to low. Bit 1, low to high. Bit 0, high to low. Bit 0, we need to go high to low again. Therefore, at the start of the pulse or signal element, we go up, and then high, low. So we've got a transition always in the middle of the signal element, or the pulse duration. Bit 0, high to low. Bit 1, low to high. And a variation is differential Manchester. Let's go to the definition. Always a transition in the middle of the interval. So similar to Manchester, we always transition from one level to another in the middle of the interval, here. If we have a bit 0, we have a transition at the start of the interval as well. And a bit 1, we do not have a transition at the start. So we're always going to change in the middle, but if there's a bit 0, we'll also change at the start. What do we get with a bit 0? Where do we start? I think we start at a low level, as we see here. Start at a high level. Assuming we start, or the previous level was high, with a bit 0, the rule is that we're going to have a transition in the middle, and we're going to have a transition at the start. At the start means here we're going to change the level from high to low, and then in the middle we're going to change. With a bit 1, at the start we do not change the level. So we maintain it, but in the middle we will change. So for every bit in the middle of the interval we will change the level. Bit 0 we will change at the start and in the middle. Bit 0 change at the start and in the middle. Bit 1 do not change at the start but change in the middle. Bit 1 do not change. Sorry, I'm losing the scale here. Bit 0 change at the start and in the middle. Same with bit 0. Change at the start and in the middle. Bit 1 do not change at the start of the interval, only in the middle. Did I get it correct? You'll see the answer. Hopefully it corresponds to the one here. There are other encoding schemes. These are some of the main ones, and we see them in examples or systems we use today. You don't need to remember them all for the exam, but you need to be able to, for example, encode some data, that is, write the signal given the data. If you're given a description of them, you should remember the first two, I think. Non-return to zero level and invert on ones. So you should remember them. The first one we've used throughout the course already. The second one is similar, except we always invert on bit ones. The others, and even if there are others that are not shown in this slide, in an exam, if you look at last year's exam, I'll give you the description. I would give you this, or some words similar to this. And from that, you should be able to create the signal given some data, or given a signal, create the data, get the data back. Why do we have all these different schemes? What are the trade-offs between them? There are several listed here. The spectrum that these signals generate differ. Depending upon the signalling encoding scheme, they generate signals with different frequency components. One aim is to minimize the high frequency components. So that is, minimize the bandwidth required for the signalling scheme. One of the later plots, I think this one, compares some of those signalling schemes looking at the bandwidth required. Without explaining it, the further we go here, the higher the bandwidth required for that signal. So we can see non-return to zero require a bandwidth up to here, but most of the energy in this is in this portion here. With AMI and pseudo-ternary, we get this. So the bandwidth is this area. Manchester and differential Manchester, higher bandwidth required. If you compare, then this is larger than the AMI and pseudo-ternary. Non-return to zero normally requires high bandwidth as well. So the amount of bandwidth required for these signalling schemes differs. We want a scheme that minimises the use of bandwidth. And in fact concentrates the power in the middle of the bandwidth, similar to what these two do. You see that most of the power, if we go up, is concentrated in the middle, whereas here it's spread out with Manchester and differential Manchester. So there are trade-offs there in terms of the bandwidth used by the signalling schemes. We've seen one of the trade-offs, error detection. We saw bipolar AMI has this inbuilt error detection. If you receive a signal which doesn't match the rules, like we had here, the rule was alternate between ones. If we don't get an alternation between the two ones, then we detect an error. And we can use that to fix errors later. So inbuilt error detection is useful for some of the schemes. Clocking and synchronization is an issue. When we transmit a signal, note that we transmit for a pulse or a signal element for some duration of time. That is, we transmit at -1 volts for 1 millisecond, for example. And then for the next 1 millisecond, +1 volts. Getting that time, or both the transmitter and receiver must know the time, and importantly, the clocks used by the transmitter and receiver should be accurate. What do I mean by the clocks being accurate? Let's say the source that sends the signal has a clock which is perfect. And the idea is to transmit a signal at one level for 1 millisecond. So this is 1 millisecond. And they send a signal, and then the next 1 millisecond sends, say, at a different level. This is 2 milliseconds. If they have a perfect clock, then they will transmit for exactly 1 millisecond. The receiver, when it receives a signal, maybe its clock is not perfect. What that means is that for the real duration of 1 millisecond, the receiver thinks it's only, well, measures it as only, say, 0.8 milliseconds. That is, how do we draw it? If this is the real duration of 0, 1 millisecond, 2 milliseconds, the receiver's clock is such that, okay, if we start here, it thinks this is 1 millisecond. When in fact, in real time, it may be slightly less than 1 millisecond, say 0.8 milliseconds. That is, its clock is wrong. It doesn't have an accurate representation of time. What that does is introduces potential errors as we receive the signal, because the receiver thinks the first 0.8 milliseconds is the first pulse, and then the next 0.8 milliseconds, which takes us to 1.6, is the second pulse. And if we have a third pulse here and a fourth one, this is at 2.4, so the receiver thinks 1 millisecond, this is 1 millisecond, but in fact in real time it's only 0.8 milliseconds because its clock is wrong. So each pulse in real time would be 0.8, 0.8, 0.8, 3.2. Let's say in the middle of the interval, the receiver records the value and converts it to a bit. So at time 0.4, what is the value? It's low. If we use non-return to 0, that corresponds to bit, this is the transmitter bits, 1, 0, 1, 1, low, high, low, low. This signal is low if we measure here, therefore if it's low, it's bit 1 received. It measures in the middle of this interval at time 1.2. At time 1.2 is about here. The signal is high, bit 0. Then in the middle of this interval at time 2.0, not a good example, but let's say it measures at this point, low, so it's a bit 1. And then at 2.8, we have about here, we have low, which is 1, and 1 more bit. Actually change this one. It measures in the middle of this interval at 3.6. What do we get? At time 0 to 1, 1 to 2, 2 to 3, 3 to 4, we get 1, and at 3.6 we get 0. Did we get it correct? 1, 0, 1, 1, 0. Why have we got an extra 1 here? When we transmitted 1, 0, 1, 0. Because the receiver's clock is incorrect, it's measuring the signal at the wrong time. So the transmitter transmits for 1 millisecond each pulse, but when the receiver receives, it measures, it thinks it's 1 millisecond, but in fact its clock is wrong and it's actually measuring every 0.8 milliseconds. And as a result, it's possible that it will measure the wrong value for a particular bit. So if the clocks become unsynchronized, the clock at the transmitter and the receiver are not correct, they have a difference which is large, then it's possible for the receiver to measure the signal which is the wrong value, i.e. a bit error occurs. Some of the signal encoding schemes allow the receiver to synchronize the clock to avoid these problems. especially, for example, the Manchester encoding. Because there's always a transition, the receiver, when it receives a transition, it knows that it's the new interval and it can synchronize its clock. But with, for example, non-return to zero, if we transmit a sequence of zeros with non-return to zero, we transmit our signal, which is always at +1 volts. A long sequence of zeros, the signal transmitted will be at the same level for all those bits. There's no opportunity for the receiver to synchronize its clock in that case. It doesn't know where one bit ends and the next bit starts. But if we have transitions, like with Manchester and differential Manchester, even if we transmit a long sequence of zeros, there will always be transitions with Manchester. There will always be changes. So the receiver can work out where one bit ends and one bit starts. So with some schemes, we can synchronize the clock at the receiver, avoiding errors. With other schemes, we cannot synchronize the clocks, and therefore, if the clocks are wrong or differ by some amount, then we can get bit errors. Another trade-off is that some are harder to implement in terms of complexity. We normally desire a small signalling rate. The higher the signalling rate to get the same data rate, the more complex it is to implement, and the higher the cost. The Manchester schemes are changing often, every or 2 times an interval in some cases, whereas the other schemes are changing just once per interval. Therefore, there's more complexity involved in the Manchester and differential Manchester encoding. So some of the trade-offs between the different signalling schemes, the bandwidth that they occupy, the ability to synchronize clocks at the receiver is good, the ability to detect errors at the receiver is good. Some are simpler than others and therefore less complex to implement and cheaper to implement at the receiver and transmitter. To finish, there are some other schemes that we will not go through that modify the bipolar AMI and the Manchester to cope with these problems, where if we have a long sequence of zeros, we can get unsynchronized clocks at the receiver, or a problem with the receiver. Therefore, there are schemes that are listed somewhere on this one, B8ZS and HDB3, which modify bipolar AMI to avoid such sequences. They are described here, we will not go through them. What we want to finish, where are they used? Some quick examples of where they're used in practice. USB, ITS323 serial ports are examples of using non-return to zero for sending our digital data as a digital signal. Ethernet, wired LAN, used, so for our computer, uses Manchester encoding. Some of these others, which we just mentioned, HDB3, are used in some long-distance wide area network links, which we haven't mentioned yet. So these are used in practice today for providing the conversion of digital data into a digital signal. It's not always this simple case of bit 0, one level, bit 1, another level. There are alternatives.